So the next speaker is Kévin Martins from the University of Bordeaux. Kévin, are you here?
Yes. Can you hear me?
Yes.
Yes.
Hi, everyone.
Hello. Can you try to share your screen?
Yes.
Perfect. Can you maybe?
Do you see everything?
Yes. Is it? Can you put it in presentation mode, full screen, or yes? Perfect. So, Kévin, the floor is yours.
Okay. Thank you. First of all, thank you, Henrik and Mario, for inviting me. As Philippe said earlier, it's a great opportunity for me to present my work here, and so I'm very glad about it. I'm Kévin Martins. Currently a Marie Curie Fellow at the University of Bordeaux, working on lead battery with Philippe Bonton. Today, I would like to talk to you about non-linear and non-hydrostatic processes in surface-on waves, and the new insights that we got recently based on lidar observations in the field. So I'll start very briefly about the wider context. I don't see it as a list of potential things, but let's say the key questions that we can answer with lidar technology, especially. So the context is that the forces induced by breaking waves are the primary driver of nearshore dynamics, and so it's very important to be capable of measuring waves and their transformation in the nearshore. I've highlighted a few very interesting questions. The first one being, how high do surface-on waves actually get? I'll come back to the actually in a moment. This implies being able to measure the surface elevation accurately, getting insights about extreme waves so that we can design structures in the nearshore. Second question that are interest me very much this moment because of my Marie Curie project. How fast do surface-on waves propagate? The first question is about the description of the energy flux, but also the link that there is between water depth and the celerity, for example, of the waves, so that we can get bathymetry insights. Lastly, where and how fast do breaking waves dissipate their energy? Because they force the circulation and the mean fluctuations of the mean water level, it's very important to be able to predict this and to quantify this process. Eventually, the nearshore circulation drives the sediment transport, so that's a key thing actually to answer. Today, we're principally interested in the first point, and the basic question is how accurate actually can we get the surface elevation, because that's the main quantity that we measure in the field. The traditional approach uses pressure transducers that we deploy near the seabed. And there are a few options to reconstruct then the surface elevation from that, and we'll see them basically here in the case of irregular waves. The first one is the simplest, and so it's the assumption that the pressure field is hydrostatic. So we measure the pressure at some height above the seabed, and basically by neglecting all the vertical acceleration terms, we are able to reconstruct the zeta, which is our surface elevation. The problem with this reconstruction, obviously, that it neglects all the vertical motions induced in surface-on waves. And so very early studies such as that of von Dorn in '78 showed that in fact the hydrostatic reconstruction underestimated consistently the height of the wave crests, whereas the troughs were very well described. And this was confirmed in the '80s with other data from Battias, for example. And so the key result of his study basically was that everywhere in the surf zone, we could expect underestimation of the energy of waves, their skewness and asymmetry as well. So basically the shape. So it was a poor description of the very skewed and asymmetric shape of breaking waves in the surf zone. It's only really after the shoreline that the hydrostatic assumption can actually describe the height of bores that run up and down the beach. The second option is to account for non-hydrostatic effects with the linear wave theory. So we start from the hydrostatic reconstruction and we correct it based on a linear transfer function that assumes an exponential decay across water depth. And so basically it's a function of the wave number Most of the time we miss this information, and so we use the linear wave dispersion relation that you recognize in equation 4 here, and that links the temporal to the spatial information of the wave field. The issues with this approach, I think, are well known now, is that as waves approach breaking in the surf zone 2, there are significant transfers, non-linear transfers of energy towards high harmonic. And the consequence is that these high frequency components, they become bound to the principal ones. And so they travel at the same speed. And that's what you can see here. So basically, these dots are dominant wave numbers extracted from highly resolved lab datasets recently published from the GlobeX experiment. And so they just show you that, in fact, most components before breaking travel more or less at the speed of non-dispersive and non-linear shallow water waves. Whereas the linear wave dispersion at high frequency strongly overestimates the dominant wave numbers. The consequence of that is that the transfer function then overestimates the correction to be applied to the hydrostatic reconstruction. And we then observe a blow up in the reconstructed surface elevation. So not only it overestimates the energy of the surface elevation at relatively high frequency, so here normalized with the peak frequency, but basically the second and third harmonic are already overestimated. And so there is the only pragmatic solution here is to apply a cutoff frequency. And then we obviously neglect all the energy at high frequency. And that has consequences that we'll see in a moment. The last option that was recently proposed by Bonneton et al. After the work of Bonneton in the Journal of Fluid Mechanics paper is a non-linear weakly dispersive reconstruction. So it works in time and proposes some corrections to the hydrostatic reconstruction. So it's very easy to implement. And so we have a first linear correction and then a non-linear term that is here in this form. A word on the hypothesis. So it makes the assumption of irrotational motions at the bottom of the water column, similar to the other reconstruction method. And it's designed for a dispersive, weakly dispersive waves. So basically, we advise it to use in terms of the shallowness parameter that is expressed as the wave peak number multiplied by the water depth below 0.2, 0.3, depending on the sea state. That comes from a recent experience. So the narrower the spectrum is, the further you can actually use it. But basically in the surf zone, we are about 0.1 in terms of mu squared. And so you can use it without any questions, I guess. The objectives here are the following. So it's going to be to quantify non-hydrostatic and non-linear effects in the surf zone. And for that, we're going to use like pressure derived surface elevation collected in the field combined with lidar data. So basically lidars provide our benchmark because they directly estimate the surface elevation without theory behind it. The results mostly come from this publication. So I invite you to have a read if you're interested. So starting with the data, for those who are not aware, lidars are quite amazing tools for measuring waves in the surf zone because they send typically infrared light, and so which is very well reflected by foam and bubbles or roughness that are generated at the surface of the ocean by breaking waves. And so it's really ideal because with a single instrument, you're capable of actually describing the geometric features of breaking waves. And so these two are the principal interactions that we're interested in the surf zone. So the data was collected during a field experiment while I was a PhD student in Bath, working with Chris Blenkinsop. And so we went in Saltburn by the sea and took advantage of this historical pier here to deploy the lidars directly from the pier. The beach is macrotidal, so we had to wait every mid to high tide to get the water in, let's say. and it's a dissipative site. You can see it better in the other slide. So we used, as I said, the pier's railing to deploy the lidars a couple of meters away from the pier, so that we were not bothered by these the pier's leg that sometimes generates splashes, and so the splashes would get detected by the lidars. So we just took a couple of meters, and that was fine. In the cross-shore direction, you can see that we deployed 3 of them, distant by about 20 meters, and so that we could cover a distance up to 80, 90 meters, depending on the moment of the tidal elevation. Basically, here I'm going to use the lidars combined with the pressure sensors that was really, deployed underneath, so that I could maximize the returns from the lidar data, because you get the maximum returns at nadir, basically. So here I have an animation to show you, just to give you an example of what it looks like. So at the top plot, you see the 3 individual data sets. So the beach is on the right, and waves will propagate from left to right. So you have the first one, which is the black one, the most offshore. The red is the middle lidar, and the blue one is the most onshore that actually gets the beach here. So Saltburn has the particularity to be like a composite beach. So basically, you have a dissipative part of the beach here, and combined with a shingle beach, which is much more reflective. So it's about 1 on 10 here and 1 on 50 here. And so at the bottom, you see the final product, let's say when I combine all 3 individual data sets. So I'll just, the fact that we have this reflective part here means that every time we had long waves generated in the inner surf zone interacting with this steeper part, let's say, like these funny reflected waves were actually interacting with the incident waves. And so I'll just leave it play for a moment so that you get used to the lidar data. Okay, I'll be able to play it a bit after if you want again. So an example of the work I could do during my PhD is basically with these high spatial resolutions. We could pick a few waves, extract their geometric properties as they were propagating in the inner surf zone, and so extract information such as the wave height, their speed of propagation, the steepness, so the slope of the roller, the length of the roller as well, horizontal length. And so really the striking features of the lidar is that we're capable of directly estimating the surface elevation and at an unprecedented spatial resolution and range in the field, at least for the surf zone. I'm not trying to sell you lidars, but let's say it requires a structure, which is quite an inconvenient, let's say, in the field, and the presence of foam, but for breaking waves, you should have some. So let's jump to the core of the results. The first thing I wanted to do here was to verify Van Doorn's results in the case of irregular waves in the field. So I split 2 tidal cycle worth of data into 8.5 minutes long data bursts. And then we could have the whole tidal cycle. So basically we start from a outer surf zone situations where almost none of the waves are broken into an inner surf zone case where in fact most of the waves were broken. So I computed the percentiles of the surface elevation. The 5th percentile means that we are at the trough level actually. And so we confirmed that the hydrostatic reconstruction is fine. It accurately describes the trough elevation for most waves and bursts. The 95th percentile is actually representative of the crest elevation. So basically the capacity of the hydrostatic reconstruction to accurately describe the crest elevation. And so in fact, we get a similar result as Van Doorn's, is that during most bursts, in fact, the hydrostatic reconstruction underestimate by 20–30% the elevation of the surface elevation. And so, yeah, in terms of variance, skewness and asymmetry, we get more or less similar results as Van Doorn's, and I invite you to go in the paper to have a look at the numbers. Next, I extracted 2 extreme cases in these all data sets. So the first one being in the outer surf, and the next one is going to be in the inner surf zone. So the first one, outer surf zone, is characterized by water depth of 2 meters, 0.15. About 10% of the waves are breaking at that location. And so basically we can quantify the non-hydrostatic and non-linear effects by comparing the different reconstructions. So in this figure, I show you the surface elevation power spectrum. And so the orange one is the hydrostatic. The lidar one is the black one. And so basically by differentiating the orange with the black one, you can actually notice that at high frequencies, the hydrostatic reconstruction misses about 2 orders of magnitude of the energy. And if you consider that most components travel at the same speed and that they are bound in the unsurf zone, it explains why, in fact, it underestimates the peak, the crest elevation. In red, you see the reconstruction given by linear wave theory that employs the linear wave dispersion. And so it blows up as described earlier. And basically it explains that because it's going to miss all this energy here, because we have to apply a cutoff at this frequency, this skewness and asymmetry, for example, are poorly described with this reconstruction. We also underestimate the variance of the surf elevation. So in terms of energy, total energy, it also has some consequences. And basically, we need the nonlinear reconstruction to be able to actually estimate energy levels at all frequencies. By differentiating the green and the blue one, which is actually the linear weakly dispersive reconstruction, you can actually understand how strong the non-linear term of the reconstruction is. So now to the next example from the inner surf zone. Basically, in this region of the surf zone, the hydrostatic pressure field is an assumption which is very often made. And to our surprise, we saw that, in fact, the hydrostatic reconstruction misses a lot of the energy also at high frequency. We still get a blow up, which occurs much far, let's say, in frequency from the linear the linear reconstruction, but it still does happen. And in this situation, strangely, the nonlinear effects are much weaker, and you can see this in the differences between the green and the blue line. And so basically, the nonlinear weakly dispersive reconstruction is capable again to reproduce all energy at all frequencies here of interest. And there are some metrics here that assess this in a more quantitative way. At the wave-by-wave scale, it's very interesting to see the consequences of whether or not the reconstructions are capable to describe the energy at high frequencies. So basically, the hydrostatic and linear reconstruction, they completely miss the extrema. So basically here, I showed a breaking wave. Really, it was at the point of breaking. And so they underestimate the wave height about 30%, which is a figure that I was also showed for other data sets. And so the nonlinear weakly dispersive reconstruction is capable of describing this. It's still underestimated a bit, but it's much better than the other two methods. In the inner surf zone, the fact that the nonlinear reconstruction, the fact that it actually describes the energy everywhere, means that it's capable of describing the sharp crested shape of the broken fronts here. And compared to the other two methods that smooth the wave front, we're actually able to describe this little bump that forms at the front of these long waves propagating in the inner surf zone. And so basically, if at every single wave, the classic approaches, which are hydrostatic or the linear reconstruction, miss all the wave crests, it means that in terms of wave height distribution, for example, we're missing all the extrema. So in summary, we confirmed the results, let's say, that Van Doorn got in the lab. And so non-hydrostatic and non-linear processes are found significant everywhere in the surf zone. These effects in the inner surf zone, they concentrate around the front, which is kind of known now. The hydrostatic and linear reconstruction, we know that they miss all the extremes, which has consequences in terms of wave height distributions. This is a bit more further investigating this reference that is provided at the end of my presentation. And in terms of errors, we expect errors of the order of 10% in terms of the variance, so second order moments, and which means energy too. And it's much higher in terms of third order moments, because the tail of the spectrum is very much important for these quantities. So in terms of the nonlinear weakly dispersive approach, it somehow supports the hypothesis of irrotational motions at the bottom, at least for the speeding and gently plunging breakers that we observed in the field. It wasn't tested against strongly plunging breakers, but so I don't know how it would behave, but the theory is not designed to handle such cases, obviously. It provides great perspectives in terms of getting new insights about surf zone wave heights and how they evolve across the surf zone, because that's very important, for example, to parameterize very common breaking parameterizations in nearshore models, and also getting insights into nonlinear energy transfers, because basically, if you're much more accurately describing the tail of the spectrum, you can more accurately describe also how this transfer occurs between frequencies and also in space. And so maybe it's going to be providing better parameterization in the field for that. So I arrive at the end of the presentation. Thank you.
Okay, so merci beaucoup, Martin, Kévin, for this talk. So there is plenty of time for questions. Are there any from the audience? So maybe I have one. So I know a little bit this work, but so if you go back to the measurement, so the lidar measurement, so the one where you compare the different, you have exactly this one. So here, when you zoom, so you have breaking waves. Well, what looks like breaking waves, but then you have this bumpy thing. So, and you clearly So with the reconstruction, you're able to follow this. So these are essentially still dispersive effects that you're measuring here.
Well, it's a tricky one. So dispersive in which sense? Like
is dispersion still active? Because you know that when
it's hard to say, because like if you measure, for example, the spectrum, the wave number spectrum that I showed at the beginning of the presentation shows that in fact most modes propagate at the same speed, and so it's not really dispersive effect. In fact, the weakly dispersive reconstruction, you could almost get similar results, assuming that the wave number follows basically omega over the speed of propagation, a bit like the hypothesis from Philip to pass from the spatial spectrum to the frequency spectrum. And so that means that it's almost a dispersionless phenomenon, and the rest is nonlinear behavior, basically, if that answers the question.
Okay. So these very small scale that you see here, that would not be some sort of undulation as you would see in ondular boards, for example.
I don't think so.
Okay. So are there any other questions from the audience for Kévin or?
May I?
Sure.
A question about the lidar, the measurements. To which extent this kind of instrument can be used also for 3Ds, three-dimensional wave field? Of course, this is a sort of blind. So but probably, do you think it's possible to use multiple lidars and then to combine that in order to have a sort of 3D reconstruction, or it's they are either too expensive or too difficult to combine the data? I'm sorry for this rather technological question, but I'm just curious.
I'm very interested about this question anyway. I mean, we've tested it ourselves. So there are a bunch of solutions out there that provide the lidars I've used so far are mainly 2D. So basically it's a pulse with an internal mirror that scans in just one vertical direction, if you could say that. There are other options that send a few channels. So in terms of the deployment I've made here, so you could imagine multiple channels in the longshore direction. Some solutions provide this at a relatively cheap cost, I would say. My experience is that it's much more complicated for extracting the information from there. So it's already quite a complicated data set to work with in 2D. I can't imagine in 3D, to be honest. But then, of course, it's the cost. Like, you wouldn't get the same accuracy or at least the same resolution in the longshore direction. So I think you cannot have the same resolution in both direction. Let's say both horizontal direction.
My question was that, I mean, if you, I was thinking, okay, in this case, in your configuration, you were able to install this system on, let's say, on the shoreline. But if you are in open ocean, for instance, you want to install this on either an offshore structure or on a ship, then of course you have to correct this for the ship motion. So, but then you have to measure the three-dimensional wave field. That was my question, because I was curious about the possibility to use it in open seas. That is. But thank you very much. It was very interesting, this part.
Thanks. I'm aware, just to answer a point of yours, I'm aware of a PhD thesis. I think it's Trondheim. That I think deployed a 3D lidar from a platform in the North Sea. I could find the information if you're interested.
That would be great. Thanks. That would be great.
No worries.
Thank you. Thank you very much for your presentation.